This is Group 10's Project 6, and I'm Owen Champion, followed by Patrick Niminant and then Josh Webb. Alright, so this is the gold and silver alloy after it is rapidly cooled from the liquid state using a quenching method. The structure is composed of irregular continuous cells with a random mix of yellow and white circles in each cell. These circles represent atoms of gold and silver that are trapped together in a saturated solution. Because the alloy was quenched quickly, atoms didn't have time to segregate or form distinct phases. This results in a metastable arrangement with no clear phase boundaries, just a chaotic distribution of atoms with distorted grains. And this metastable arrangement affects the alloy in a way that makes it more stable, which enhances its strength and toughness. And this is the gold and silver alloy after it is very slowly cooled from its liquid state. When the gold-silver alloy containing 40% gold is cooled very slowly from liquid state, the atoms have enough time to move and arrange themselves into their most stable configuration. And this forms the large, well-defined grains that are rich in gold. These big yellow circles, that's what it shows. And around these grains, a fine layered structure developed where gold-rich and silver-rich regions alternate in thin bands. This layered pattern is called a eutectic structure, and it appears because the alloy composition is close to the eutectic point in the phase diagram. The slow cooling allows complete separation of two types of regions, producing a balanced and orderly mixture that minimizes the system's energy. This slowly cooling method also reduces the alloy's strength, but increases its ductility and allows it to undergo significant plastic deformation without breaking.
Okay, now for question 2. So for question 2, we have now we have 1 kilogram of gold and silver mixture. 40% is gold and 60% is silver. We cool it from 1200 Celsius to 1000 degrees Celsius. Now, this slide will be focusing more on question 1, or question A, which is what phases are present? Okay, so first we begin with 1 kilogram of that alloy, which is 40 gold, 60 silver. The alloy initially at 1200 degrees Celsius is fully a liquid. And as it cools down to 1000 degrees Celsius, we need to figure out what phase or form, how much each phase is present, and how the gold is distributed to them. So this is going to be mostly on the phase diagram of gold and silver, which shows us how the composition and temperature can control the balance between liquid and solid phases. So at 1000 degrees Celsius, the alloy composition, the gold aspect of it lies between the liquidus and solidus lines on the phase diagram, which means that this is a two-phase system region. So, or I should word it better, the system is in a two-phase region there. So the alloy is no longer fully liquid. Instead, it contains both liquid and solid phase. So the alpha phase is a face-centered cubic, which is FCC, which is solid solution of gold and silver. So basically, it's just a mixture of solid and liquid, and it's cooled, and it's in the mushy zone. So it's where solidification begins, but it's not complete yet. Okay, so for this question, we are going to be covering question 2, part B and C. So part B asks us what is the mass of each phase. So first of all, this is going to be using lever rule. So for lever rule, first of all, let's write down our givens, or the values we're going to be plugging in. So write down CO, which is Gould's overall fraction, which would be 0.4. CS is Gould's fraction in solid, which is 0.47. CL is Gould's fraction in liquid, which is 0.29. Now that you have your um, units or variables that you're going to be plugging in, our lever rule equation is CO minus CL divided by CS minus CL. So it's Gould's overall fraction minus the Gould's fraction in liquid divided by Gould's fraction in solid minus Gould's fraction in liquid. And so what that's going to give you is the mass solid. So that is going to be 0.611 kg. That's going to be our mass solid. And for our second equation, it's going to be the mass fraction of liquid. So we found it in solid, now we're finding it in liquid, which is 1 minus our mass solid, which we just got, which is 0.611, equals CS minus CO divided by CS minus CL. Or, I'm sure you can figure that out, I don't need to repeat it, but when you plug that in to find that, you get our mass liquid is 0.389 kg. So now that we've completed question B, which is to find the mass of each phase, found the mass of solid and the mass of liquid, now what we need to do is question number C. What are the Gould mass portions of each phase? So Gould in solid mass is going to be our Gould's fraction in solid multiplied by our mass solid. So that is going to be our Gould in solid. That's going to be 0.287 kg. And our Gould in liquid is going to be our CL, which is Gould fractions in liquid, which is 0.29, multiplied by our mass in liquid, which is 0.389, which gives you 0.113 kg. So that's the answer for B and C. So for question number 3, we have explain how we can use gold-silver alloys to make memory devices to mimic brain memory. Which alloy combination would be better? Gold-silver alloy or copper-nickel alloy, and why? So when we talk about this first, let's talk about the gold and silver alloy. Silver is one of the two metals commonly used in conductive bridge memory because silver ions are mobile, and they're mobile in many solid electrolytes, and they can form metallic filaments under an electric field. So silver electrodes are frequently used in these types of devices. So gold is not very prone to oxidation, and it's also not typically used as the mobile ion. So because they're less mobile and they're expensive, gold is often used to stabilize surfaces. Now let's talk about copper and nickel. Copper is commonly used it's commonly used as a mobile ion source. Copper ions are readily formed and they migrate and many solid electrolytes, and copper is cheaper than silver. So that's obviously better. And nickel is almost the same as gold as a stabilizer. Um, so they're both they're both kind of the same, but the only advantage I'd say copper and nickel really has is that it's lower cost, and copper can supply ions more efficiently and it's more compatible with certain things.
Finding the density of gold and silver in the FCC structure is converting radius to lattice parameters for both metals. First, one must know in FCC atoms touch along the face diagonal and not the cube edge. They must also know the geometry of a face. A square of side A has a face diagonal of length square root 2A. Along that diagonal, you span half a corner, one full face atom, half a corner atom, for a total linear contact length of 4r. So, the square root 2a equals 4r, therefore a equals 4r over the square root of 2. Unit cell mass. Mass per atom, m over Na, where Na is Avogadro's number. Mass per cell is 4, so it is 4m over Na. This converts grams per mole to grams per atom and multiplies the number of atoms in one cell. To find the unit cell volume, one must cube A. By doing this, area is converted to volume. This will allow us to find the density, which is measured as mass over volume. To find the density, the unit mass found in step 1 will be divided by the unit volume that was found in step 2. This gives the answer of 19.3 grams per centimeter cubed for gold and 10.6 grams per centimeter cubed for silver.